So in this second lecture, we will start the formal study of topology, starting with set theory and logic. Set theory and logic are something foundational in mathematics, and almost all of modern mathematics is built upon these two things. And topology is no exception, so we have to study a little bit of set theory and logic to really get into the ideas of topology. So what is a set in set theory? Let's start with that. So a set is a collection of objects. Of course, these things you must have already seen before, and intuitively it is clear what a set means. You gather some objects of the same kind or various kinds and put them together in one object. So that object is called a set. For example, the set of black cats is a set. The set of all people living in India is a set. And you can also have different kinds of things taken together, such as set of black cats and brown dogs. So that is also a set. And once you have a set, you would like to perform some operations on it, and these are called set theoretic operations. So let us describe them one by one. So let's begin by describing set operations using two sets, A and B. But before we do that, let's fix some notation. So the first one is that if an element or member, so element just means a member of a set, belongs to some set A, then we write X belongs to A. So this notation stands for belongs to. Okay, so this is the first one. Another is that if all elements of a set B, of a set A, let's say, are also in another set B, then we write A is a subset of B. So this is the notation for subset. And if A is a subset of B and B is a subset of A, then we write A equal to B. So this is of course equal to, and it just means that we have two different symbols. So A and B are symbols for the same object. Same object. So there are two symbols for the same object, in which case we have equality. So these two conditions just mean that all elements of set A are in set B, and the second one means that all elements of set B are in A. Okay. Just as a remark here, let me write that we allow the notation A as a subset of A. So of course A is equal to A, but we also allow this notation which views A as a subset of itself. So if you go back to the definition, the notation for the subset, if all elements of the set A are also in another set B. So here we allow B to be A as well. Okay, so this case is also allowed. If we want to distinguish it, if we want to distinguish what's called a proper subset, for proper subset, what do I mean by a proper subset? So a proper subset A of a set B is a subset, first of all, of B which does not contain at least one element or one member of B. So for example, you have the set A, let me write 1, 2, and B can be 1, 2, 3. So here also this is part of the notation. A set is usually written with this curly braces, and you will see that we will also define sets using this notation. And in this case, when A is 1 and 2 and B is 1, 2 and 3, we write A is a proper subset of B using this notation, proper subset. This notation convention is not universal, in the sense that some authors use the second one, which we have used for proper subset, to mean what we have denoted by A is a subset of B, which allows B to be A itself. So some authors use just this proper subset notation to mean just a subset, and this is a good time to mention what book we will follow for this course. So book to follow for this course, this is the book titled Topology, and the author is James Mumkress, and this is a widely used book, and you will easily find it available in your libraries. And we will by and large follow this book. Some parts might be from other sources, but most of the material for this course is following this book. Okay, and in this book, like I said, some authors use just this notation. A is a subset of B means for us A is a subset or equal. Okay, so Mumkress uses this notation to mean A is a subset, proper subset, or it is equal. Okay, and in Mumkress there is also another notation like this. Let me rewrite it. So like this. So when the lower horizontal bar is cut, means for us A is a proper subset. Okay, so here this one is used in Mumkress, and he calls it proper inclusion. So this subset notation is also called inclusion, and For Munchausen, this is proper inclusion, and the first one is simply inclusion. So now let's go back to the set theoretic operations with these two sets A and B. So the first one we will consider is set union, or simply union, and this is denoted A union B. So this is the notation for union, and it just means that this is the set of all elements which are so either of these three conditions. Okay, so there are three conditions. First one is that it can be, so if an element belongs to A but not in B, similarly might belong to B but not in A, or it can also belong to both these sets A and B, both A and B. Okay, so in terms of Venn diagrams, so if you have two sets which we depict by these circles A and B, so the union is simply the set, this shaded region which takes care of elements both inside A and B. So this region on the left with the red one, this is A but not in B, and in this region in the blue one, this is B but not in A, and in this middle one, this is both A and B. Okay, and all these three conditions, any of these three conditions, if they hold, then this element is said to be in the union. Okay, and in terms of symbols, mathematical symbols, we write as follows. So X such that, so this vertical bar is a notation which is pronounced in words as such that X is in A or X is in B. Okay, here or does not exclude that it can be both in A and B, as we have seen. So usually in normal day-to-day language, we might mean for example day or night, so it cannot be both, but here it can be both. Okay, so or does not exclude this possibility that we can have X belonging to both A and B. Similarly, we have other set operations. So set intersection, which is really just the third one here, which is both A and B. Okay, so this is the green shaded region in this picture, in this Venn diagram, and so we write A intersection B like this with an upside down cup symbol. This is intersection, and this is the set of all elements such that X belongs to A and X belongs to B. So this is how we write it. Again, we read that this is the set of all elements X such that again X belongs to A and X belongs to B. So this, in notations, in mathematical notations, we write it like this. So like we saw, if you have the Venn diagram, then this is just the intersection of both A and B is where they overlap, the two sets overlap. Okay, set difference is another operation, and here also we have already seen it, which is in Venn diagram form. You have two sets, then the set difference is just something that belongs to one set but not to the other. So we write it either A minus B like this, or also A minus B is written like this, and this in mathematical terms is written as the set of all x, such that x is in A and x is not in B. So here I am using another notation, does not, which means does not belong to, which is the opposite of this belongs to notation, and it is used, and this straight line that cuts through this symbol means it does not belong to B. Okay, now we have seen these set operations for two sets A and B, and let's talk about what are called arbitrary unions and intersections, and this is for many sets taken together. Okay? And we will call this a collection. So collection is a number of sets taken together. Okay? And this collection can be arbitrary. So this is where the term arbitrary union comes, or intersection. So this collection can be arbitrary in the sense that this number of sets can be arbitrarily high. Okay, and an example of a collection is the collection of all subsets of a fixed set A. Okay, and this in fact has a specific name. This is called the power set. The power set of A, and usually denoted by PA. Okay, so when we say collection, it can also mean a set whose elements themselves are sets. Okay, so a collection is a set whose elements are sets. Okay, so for example, this example with the power set, each element of the power set is itself a subset of A, so it is a set. Okay, and this arbitrarily many term can be used, for example, for the collection of 1-point sets formed from real numbers, from the set of real numbers, and so each real number R, you take a real number R and you form a set containing just that real number, and this is a subset of R. Okay, so this is the real numbers, set of real numbers, and the collection of all these sets is infinite. Okay, because you have infinitely many real numbers, the collection of all 1-point sets formed from the set of real numbers is going to be infinite. And in mathematics, we also distinguish between the types of infinities. For example, you can have the set of natural numbers as well. And if you take the collection of 1-point sets of natural numbers, then also it's going to be an infinity, but that infinity is in some sense smaller than the infinity that you get from real numbers. So there are various distinctions between different infinities, and we will see this later on. But when we say arbitrarily many, it can mean any kind of collection that can be formed from collecting different kinds of sets. Okay. So when we have a collection, so let A be a collection, then we can form the arbitrary union of sets in this collection A, and this is usually denoted by something like this: A in this collection A with these elements which are themselves sets. Okay. And this is defined to be the set of x's such that x belongs to A for at least one A in this collection A. Similarly, you can define the intersection of all these sets in the collection, which is x belongs to A for all all sets A in this collection A.